Welcome. So Brisk is about Hadoop powered by Apache Cassandra, and it's about solving two problems. One is solving the reliability and scalability problems of HDFS, and the other is about bringing analytical and real-time workloads to a single system with no ETL required. So for the first of these, an HDFS-based Hadoop stack is very good about dealing with failures of these processes on the right here. But the processes on the left, failure of one of those causes problems, usually requiring some kind of manual recovery. And the big one of those, kind of the turtle upon which all the other turtles stand, is the name node. And the Office Space guys kind of described how a lot of us feel about the name node. There's two main problems there. One, of course, is the failover and reliability story, but the other is the scalability problem, which is that the name node has to be able to hold all your file system metadata in memory on a single machine. So that causes pain as well as your clusters get large. So Brisk fixes this by building on Cassandra instead, and by bringing all of these different functionality into a single fully distributed stack, meaning that each node in the ring in the cluster is running the same set of services. So to do this, what Brisk does is it adds a couple things to the combination of Cassandra and Hadoop that you get by just kind of shoving those together. Cassandra's been able to provide its data out to Hadoop and MapReduce jobs for about 1.5 years now. But one of the components that Brisk adds is a file system built on top of Cassandra that Hadoop can interact with. So Brisk is built on Cassandra 08 and Hadoop 20.203. So we think that the revitalization of the Apache Hadoop releases is a good thing, and we look forward to participating with that. A little bit of background about Cassandra to understand how we're going to build this Cassandra file system that Hadoop can talk to. First of all, Cassandra is built around a fully peer-to-peer replication. So each node in the cluster knows where each row or block should be located and can route requests accordingly. Once a request is routed to a node that owns a replica of that data, Cassandra manages that by dealing with the local file system. It's locally managed storage and replicated around machines with a peer-to-peer design. So when a request arrives for a write on a Cassandra node, we batch those requests up into a structure called a memtable, which will be familiar to anyone who's read the big table paper. And when the memtable gets full, we write that out to disk in streaming I/O. So there's no random I/O on writes at all. One of the other consequences of doing this directly with locally managed storage is that it's very easy to make it fully durable with a commit log-based design that's been around for years. There's no magic there. It's your typical commit log durability design. So the data model for Cassandra data is based around rows which have columns. So it's similar to a relational table, but the big difference is that the Cassandra storage model is sparse. So there's two consequences of having a sparse storage model. One is that when you add a new column to your data model, as we've done here, so everyone has a name and a password, and then we added in a site field later. So when we add that in, we don't have to go and reallocate the storage for the existing rows. We can just start using that new column immediately. So that's one of the consequences of having a sparse storage design. The other is more dramatic, which is that we can actually use column names that are only known at runtime and just kind of dynamically allocate those into a row. And typically in a real-time oriented Cassandra application, we'll use this to build materialized views out of rows that that are basically pre-computed result sets for specific queries. But we're also going to use this in the Cassandra file system as well. One other point I'd like to make here is that sometimes Cassandra gets called schemaless, which isn't quite true because, first of all, you do have this concept of column families, and you do have columns within column families, and you can attach type information to those columns. So it's more of a schema optional than schema-less design. So putting these together for the Cassandra file system design, on the left, we have sort of the abstract view of what we're doing. We're storing a file named file.txt, and there's an inode that knows where blocks are that contain the file.txt data. Then on the right, this is how it's broken down into different column families. So there's actually two column families involved. There's the inode column family that knows where the blocks of data are, and then there's the subblocks column family, and I'll get to why it's subblocks in just a second. But starting with the inode column family is an example of a column family where all the rows have basically the same set of columns. We have a file name column, we have a data column. So in this case, the file name is file.txt, the data is a list of block IDs. Now, one wrinkle here that I'd like to point out is that we are looking up, we're effectively doing, when I want to read file.txt, what I effectively do is I say select from inode where file name equals file.txt. So I'm looking that up with an index that's on the file name column. And this is a native Cassandra secondary index. So the reason that we do it that way, instead of using file name as the natural key for the row, is that the row is the unit of atomicity that you get in Cassandra. And so in particular, this affects renames. So if file name were the row key, and we went to do a rename, what we'd have to do is we'd have to copy that data into a new row and then delete out the old one. So if you hit the right set of failure conditions, you could end up with, in fact, 2 rows. Or if you did it the other way around, you could end up with 0 rows, which is worse, so you wouldn't want to do that. But by doing it this way with the surrogate UUID key, then we get atomic renames, and everything works without that corner case. Now the subblocks column family, now I mentioned that we're breaking those blocks up into subblocks, and the reason for that is Hadoop prefers to have a relatively large block size. So in Brisk, we default to 64 megabytes. But it turns out that when you're hitting the system with these very large write chunks, 64 megabytes, pause, 64 megabytes, pause, that doesn't work as well as if you're hitting it with smaller chunks continuously. So we break the blocks up into 2 megabyte subblocks. So it's 2 megabytes, 2 megabytes, 2 megabytes constantly, and it smooths out the workload. That's what's going on there. So coming to the other part of Brisk, which is unifying real-time and analytical workloads, this brings us to the second piece of software that was written for Brisk, which is the Brisk Snitch. Now in Cassandra, the snitch is the system that tells the cluster where or what groups each machine belongs to. So in a typical Cassandra deployment, this will be racks and data centers for multi-data center scenarios. But it applies just as well to an analytical group of machines and a real-time group of machines. And the reason why you want to do this is that you don't want to mix analytical and real-time workloads on the same machines. Because if your application is doing requests and all your hot data is cached, everything's going really well, then all of a sudden a MapReduce job starts sequential scanning through everything, evicting your application data from the page cache. That's bad. And on the other way around is bad too, because you're trying to sequential scan through your data and you keep getting interrupted by having to go seek for requests that are coming in from the app servers, and so your throughput is damaged on the analytical side as well. So you really want to separate those out, let each side have a full copy of the data set so it can do its thing without interfering with the other, and then Cassandra takes care of replicating between the two. It's bidirectional replication. Both from the real time to the analytical side and from the analytical side back to the real time. And we'll see an example of doing that in a few minutes. One of the other things I wanted to point out here is that Brisk has full knowledge of data locality about the Cassandra data. So all these Hadoop task trackers, those are doing tasks against the local data that's stored on the Cassandra node that they're dealing with. And this generalizes to however many copies you've asked Cassandra to make of your data. In particular, it's flexible about how many copies I have of both sides of the workload line. For instance, I might have 3 copies of my user accounts data on the real-time side and 1 copy on the analytical side. But then once my user activity history column family, I want to keep the full log of that on the analytical side. But on the real-time side, maybe I only care about the last 30 days. So I could have 3 copies of the historical data for redundancy on the analytical side and 0 copies on the real-time side. So it's very flexible that way. So when we start moving up the stack past above the raw MapReduce layer, Brisk also does some application customization there as well. Everyone gets the Cassandra file system interaction basically for free because that's a common interface. Providing insight or the ability to work with the native Cassandra column families and rows and columns, that's custom per application. So that's one of the things we did. And then the other is it basically depends on the tool. So in Hive's case, the big one that we did was the Cassandra native Hive metastore. So instead of having to have Derby or a MySQL database off somewhere that you need to back up and worry about failover if it goes down, there's a Hive metastore that persists directly to Cassandra. Everyone gets that unified view of the schema with the full redundancy and availability of Cassandra behind it. One of the other things that the Hive metastore in Brisk does is it reflects Cassandra column families out to Hive automatically. So by default, you will get, as Hive tables, views of the Cassandra column families that your real-time application is working with. Now, I mentioned earlier that Cassandra is schema optional. And Hive is not schema optional. Hive is schema required. So you can, if necessary, you can go in, as with these bottom 2 examples, and give to Hive any missing schema information necessary. But typically, you can just let it reflect it and do its thing, and that works fine. And then, of course, here on the top, we also have an example of a Hive table that's stored in the Cassandra file storage. Similarly with Pig, the interesting thing about Pig is that it's actually, Pig support for Cassandra is actually older than Hive support. But it's definitely a frequently asked question that you'll see on the mailing list a lot is, hey, how do I get Pig to work? Because there's a bunch of dots to connect. And you can see here the different environment variables you have to set up. And that's kind of the tip of the iceberg. And Brisk unifies that and gives you the full stack support. All you need to say is Brisk Pig, and you get your grunt shell. Pig also supports load func and store func for native Cassandra column families. Both Pig and Hive, incidentally, if you're familiar with Cassandra, you know that there's this other concept called a super column, which is basically a column with subcolumns in it. And it's useful for those materialized view rows. That's basically what it's useful for. I won't go into details here other than to say that both our Pig and our Hive support are compatible with super columns and know how to deal with those. I'd like to, at this point, talk about a more concrete example. This is a portfolio manager application. This is part of the Brisk distribution, is this demo application. And what we're dealing with is we're dealing with portfolios that each have a certain number of shares of different stocks. And so you can see that here's our first column family, is our portfolio column family. And we're using the wide row model, meaning that a row each has dynamic columns, not a predefined set of columns, but a dynamic set of columns where the column name is the stock that I have shares of, and the value is the number of shares of stock that I have in that portfolio. Then we have the live stocks column family, and that's a static set of columns. It has one column called last that has the current stock price. And then we have the stock history column family, which is, again, this is a dynamic column family where we have one row per day. And the values of the columns in that row are the values of the stock at closing time, when the market closed. So what we're going to have is, we're going to have on the analytical side, sorry, let's start with the real-time side. On the real-time side, we're going to have thousands of stock updates per second. We're going to have users interacting with their portfolios, buying and selling stocks. And then on the analytical side, every 10 minutes or so, we're going to go through and we're going to compute the value at risk for that portfolio. And we're going to have that, we're going to let that be replicated back to the real-time side and expose that to the users. So what you would see, this is what you would see when you start up the portfolio application from the user's perspective before that Hive job gets run to compute the value at risk. So you can see here that we're getting the portfolio value and the percent change today. And this is a very volatile market, by the way, that we're seeing on this slide. But you have the percent change today. That's coming just from the real-time side. I don't need to perform any joins or anything like that to compute those. But you can see at the bottom here, and the formatting's a little messed up as it got squished down for the slide, but at the bottom you can see that there's a question mark for the value at risk. And that's because the Hive job hasn't been run yet. So as soon as that gets run for the first time, that will be populated, and then it will be repopulated every 10 minutes. Finally, Brisk is fully integrated with DataStax Ops Center, which lets you monitor and run Cassandra or Brisk cluster, lets you add and remove nodes, lets you monitor historical and current performance, look for what is running in the cluster right now, and that includes both MapReduce jobs and Hive jobs, and see the progress on those, as well as information on the real-time side. Brisk is licensed under the Apache license. It's available on GitHub, and the second URL here is for the Portfolio Manager demo. I have time for some questions.
Is there an easy way to use Snappy with an existing instance of Cassandra without having to do an export-import with Brisk V2?
No, there is not. So Brisk Beta 2 supports snappy compression at the file system layer. Brisk Beta 1 did not, so you would need to copy that data in, basically re-import that data would be the easiest way to do it.
Okay, my question is more about like Cassandra, when you have bigger and bigger nodes, where each of your node in Cassandra is very big in storage capacity, then how do you manage to like take nodes out of the cluster? Because it might take a long time to replicate all the data, right?
So yes, that's true, but it kind of doesn't matter because replication or re-replication is not, it doesn't block other operations. And because of the storage engine design, it's never going to be doing random I/O for that replication either. It's all sequential I/O. So it's surprisingly fast on the one side. And on the other side, if I have 3 replicas of the data and I'm moving one of them to a different node, I still have 2 replicas that, that are unaffected.
Yeah, but if the node has a lot of storage space, then to move all the terabytes of data out of the remaining replicas, right, you are actually bottlenecked on a network in that case, right? Right. So the larger your data is, the longer it's going to take to move. But the point is that if it's down for 1 hour, that if it were causing badness in your cluster, you don't want that for 1 hour or for 10 hours. So it's designed so that it doesn't cause badness in the cluster, and it can coexist with ordinary operations going on at the same time.
Okay. Have you done any I/O or query benchmarks comparing HDFS and the Cassandra?
We've done some preliminary benchmarks. Brisk is even to about 10% faster. So same ballpark, basically.
What do you think accounts for that?
I don't know. Is your expectation that it would be much faster or that it would be much slower?
I thought it would be a little slower, but I don't, that's just a hunch.
Well, one of the things that was on my slide that I didn't read was that it actually doesn't go through the full Cassandra read path when it's reading from the Cassandra file system. It kind of cheats. And because it knows that since the SS tables are immutable once they're written, the record reader immats those directly instead of going through the full Cassandra read path.
Okay, so I was wondering, thanks.
So I have a question on the Brisk architecture. So in the ring that you have divided ring into 2 parts, one is OLTP and other is the analytical systems. So since MapReduce typically works on the files and blocks, and then you're storing them as sub-blocks, and then that gets replicated on the OLTP side. OLTP sides are typically having columns and the column values. So how do you match these 2 different data formats and sync them together?
That's basically up to what you're building on top of that. So usually, with Hive, for instance, it's very straightforward because Hive thinks in terms of rows and columns anyway. So it's going to turn your block data into some sequence of rows and columns. Similarly on the Cassandra side. And then again with Pig thinks in terms of bags and tuples. So it's up to the higher level to kind of make sense of how to match those together. If you were writing MapReduce jobs by hand, then you'd have to do some kind of juggling there.
And since on the analytics side, you have Cassandra nodes running on the same machine and also the job trackers running. So currently we have challenges where we want to run HBase as well as Hive on the same cluster because they have resource contention. HBase also needs memory. MapReduce also needs memory. Similar will be the case with this Brisk as well. Cassandra also needs some memory. To run MapReduce, we need memory as well as the computation power. So how do you handle this resource contention?
Well, I think the key is what I mentioned earlier, that we strongly recommend running the analytical and real-time sides on different machines. And so once you do that, to handle just the write side, Cassandra doesn't need very much memory at all. So if all you're doing is map reduces plus handling the write replications that are coming in from the real-time side, then they coexist very well.
So how do you control that the data gets replicated? Like there's a single copy on the real-time side and 2 copies on the analytical side. So
that's basically done at the schema layer in Cassandra, where when you define your key space, you would define, for instance, for the Cassandra file system, there's actually 2 key spaces for Cassandra file system. One is an archive for data that I don't expect to need to modify anymore, and another is for sort of live file system data. The reason is because we use different compaction strategies for those 2 sets of data. But you can tell it that on a per key space basis that I want Cassandra to maintain 2 copies here and 1 copy there.
So these are 2 separate clusters, 2 separate Cassandra clusters?
It's one logical cluster that's split into 2 groups.
So are these 2 separate Cassandra rings, or do they form a single ring?
I think it's most useful to think of them as separate rings, but there's a little bit of truth to both. Okay. And we could go into more detail on a whiteboard if you want.
Okay, thank you.
I kind of wanted to know about CFS, as far as there were some nice features this morning about HDFS with, mounting that, exporting it as NFS. I kind of wanted to know if there was anything on the roadmap for that where I could, instead of having to chunk data and expire rows and columns, if that was a possibility within Brisk to do that in a file-based construct so that I could expire them.
So yes and no. Yes, in the sense that you could do it. No, in the sense that I'm not convinced that exposing any distributed file system over NFS is a fantastic idea. But to the extent that it's a good idea, then you could certainly do it with Brisk if you wanted to.
Okay, thanks.
So can you handle different data retention policies on the real-time side and the offline side, the analytic side? Maybe on the real-time side, you want to keep updates, say, the last week. For analytics side, you want to keep all the updates since beginning of time. Like I'm thinking of your stocks example, right? Maybe you want just the histories from the last week for the real-time analysis and 50 years back for the offline analysis.
Yeah, absolutely. You can definitely retain data longer on one side than the other. And in fact, one of the features of Cassandra that we added for 07 earlier this year is an expiring columns feature where you don't have to explicitly remove data that you don't want anymore. You just say, when I insert this, I want you to keep this around for 30 days, for instance.